Hi, Stu Schwartz from MasterMathMentor.com. This is video AB35. The topic is inverse trig functions, and it covers the AB manual, pages 203 through 206. While inverse trig functions should have been covered in a trig or pre-calculus course, they will be covered here in their entirety because their definitions are instrumental in taking derivatives of these functions and then subsequently taking integrals that yield inverse trig functions. The inverses of the trigonometric functions follow from their definitions. To find inverses, we exchange x and y. So for instance, if we have y is equal to sine of x, shown here in red, the inverse is x equals sine y, shown in blue. It is clear that the graph of x is equal to sine y is not a function. For any value of x, there are multiple values of y. So we will restrict its range in order to make it a function. And we show this in the bold-faced blue curve. We now look at the graphs of y equals sine x and its inverse, x equals sine y, with a restricted domain. We solve for y, getting y equals inverse sine of x. Their graphs are mirror images across the line y is equal to x. We can write y equals inverse sine x as y equals arc sine x, so as not to confuse it with y equals 1 over sine x, which is cosecant x, which is a very different function. So the sine of an angle is a number. The inverse sine of a number is an angle. We next show the graph of the inverse of the cosine function, x equals cosine y, in a dashed curve. To create a function, we restrict its range and then show y equals the inverse cosine of x or arc cosine of x in a bold red curve. Finally, we show the graph of the inverse of the tangent function, x is equal to tangent y, in an infinite number of dashed curves. But to create a function, we restrict its range, and then show y is equal to the inverse tangent of x, or arctangent of x, in a bold green curve. So we now define our inverse trig functions. Y is equal to the inverse sine of x if and only if sine y is equal to x, and y is greater than or equal to negative pi over 2 and less than or equal to pi over 2. Y equals the inverse cosine of x if and only if cosine y is equal to x and y is between 0 and pi inclusive. And y is equal to the inverse tangent of x if and only if tangent of y is equal to x and y is between negative pi over 2 and pi over 2, not inclusive. As a review, here is a table of values of angles in terms of degrees and their corresponding values in radians. While many real-life problems are written in terms of degrees, remember that all calculations in calculus are done in radians. 30 degrees is pi over 6, and 45 degrees is pi over 4. You need not memorize the entire chart, as any of the special angles are multiples of 30 and 45. For instance, 150 degrees is 5 times 30, making the radian value 5 pi over 6. Two special triangles are used quite a bit, the 30-60-90 triangle and the 45-45-90 triangle. In the 30-60-90 triangle, we can let the side opposite 30 be 1. The hypotenuse will always be double that, or 2, and the third side opposite the 60 degrees will be square root of 3 times 1. So in a 30-60-90 degree triangle, the ratio of sides is always 1 to the square root of 3 to 2. In a 45-45-90 triangle, it is isosceles, so the two legs are 1 and the hypotenuse is 2. So in a 45-45-90 triangle, the ratio of sides is always 1 to 1 to square root of 2.
Here are 4 inverse trig functions that you should be able to find very quickly because of your knowledge of special angles. 1a is the arcsine of -1/2. Sine is negative in the third and fourth quadrant, and we want the fourth. And the special angle is pi over 6, so our answer is negative pi over 6. 1b is the inverse cosine of 0, and that is pi over 2. 1c is the inverse tangent of the square root of 3, and by special angles, that angle is pi over 3. D is the inverse cosecant of negative square root of 2. To find this, we take the inverse sine of -1 over the square root of 2. The answer will be negative, and our special angle is pi over 4. In problem 2, you are asked to take a trig function of an arc trig function. The best way to do this is to draw a picture describing the arc trig function in terms of theta, and then find the trig function of theta. In 2a, we're asked to find the sine of the arctangent of 3/4. We draw a picture with a quadrant 1 angle. The opposite side is 3, the adjacent is 4, and that makes the hypotenuse 5. Therefore, the sine of theta is simply 3/5. In 2b, you're asked to find the tangent of the arc cosine of the square root of 2 over 2. We draw a picture, again, a first quadrant angle, theta, with adjacent square root of 2 and hypotenuse 2, making the other side the square root of 2, and therefore the tangent of theta is simply square root of 2 over the square root of 2, which is 1. In 2c, we're asked to find the secant of the arcsine of 1/3. We again draw a quadrant 1 angle, theta, with opposite 1, hypotenuse 3, making the other side the square root of 8. And therefore, the secant of theta is simply 3 over the square root of 8. You can rationalize that fraction if you want to. 2 reads the cotangent of the inverse cosine of -2/5. We draw a quadrant 2 angle because cosine is negative in quadrant 2, with adjacent -2 and hypotenuse 5, making the third side the square root of 21. And therefore the cotangent of our angle is -2 over the square root of 21. The 4 problems in number 3 are done exactly the same way as number 2. We will draw a picture, but this time using variables. Find the missing side, and then find the trig function we are interested in getting. 3a is the cosine of the inverse sine of x. We draw a quadrant 1 angle with opposite side x, hypotenuse 1, making the third side the square root of 1 minus x squared. And since we want the cosine of the angle, our answer is the square root of 1 minus x squared. 3b reads the tangent of the inverse cosine of x. We draw a quadrant 1 angle with adjacent side x, hypotenuse 1, making the remaining side the square root of 1 minus x squared. And since we want the tangent of theta, our answer is the square root of 1 minus x squared over x. 3c reads the sine of the inverse cosine of 2x. We draw a quadrant 1 angle, and that makes the adjacent side 2x, the hypotenuse 1, and therefore the remaining side is the square root of 1 minus 4x squared. And since we want the sine of our angle, our answer is the square root of 1 minus 4x squared. 3d is the sine of the inverse tangent of 3x. We draw a first quadrant angle, making the opposite side 3x, the adjacent side 1, making the hypotenuse the square root of 1 plus 9x squared. And since we want the sine of our angle, our answer is 3x over the square root of 1 minus 9x squared. So, with the knowledge we now have, we can now generate the derivatives of the inverse sine of x, the inverse cosine of x, and the inverse tangent of x. Since y equals the inverse sine of x, then x is equal to the sine of y. We will draw a graph showing that y is the angle, making x the opposite, 1 the hypotenuse, and the third side is the square root of 1 minus x squared. We now take the derivative of x is equal to sine y implicitly, and we get 1 is equal to cosine y dy dx, and dy dx is equal to 1 over cosine y. But the cosine of y is simply the square root of 1 minus x squared over 1. So the derivative of the inverse sine function is 1 over the square root of 1 minus x squared. Note that there is no trig in our answer. For number 5, y equals the inverse cosine of x is equal to the cosine of y. We again draw a picture where y is the angle and x is the adjacent and 1 is the hypotenuse, and it makes the remaining side the square root of 1 minus x squared. We again take our derivative implicitly of x equals cosine of y, getting 1 is equal to negative sine y dy dx, and therefore dy dx is equal to negative 1 over sine y, and our answer is negative 1 over the square root of 1 minus x squared. Again, note that the derivative of the inverse cosine of x does not have trig in its answer. In 6, y equals the inverse tangent of x, we write this as x is equal to tangent of y. We then draw a picture. Y is the angle, x is the opposite, 1 is the adjacent, and the hypotenuse is the square root of 1 plus x squared. Taking our derivative implicitly of x equals tangent of y, we get 1 is equal to secant squared y dy dx, and therefore dy dx is equal to 1 over secant squared y, which is cosine squared y. And since the cosine is 1 over the square root of 1 plus x squared, cosine squared y is equal to 1 over 1 plus x squared. So the derivative of the inverse tangent of x is 1 over 1 plus x squared. Again, no trig in the answer. So we have our 3 inverse trig derivative functions. The derivative of the inverse sine of x is 1 over the square root of 1 minus x squared, and its corresponding derivative with respect to x of the inverse sine of u is 1 over the square root of 1 minus u squared times du dx. The derivative of the inverse cosine of x is equal to negative 1 over the square root of 1 minus x squared. And the derivative with respect to x of the inverse cosine of u is negative 1 over the square root of 1 minus u squared du dx. The derivative of the inverse tangent of x is 1 over 1 plus x squared, and the derivative with respect to x of the inverse tangent of u is 1 over 1 plus u squared du dx. You can also take the derivative with respect to x of the inverse cosecant x, inverse secant x, and inverse cotangent of x using the same techniques that were used on the previous slide. However, they are rarely used. You must memorize these rules. We start with taking the derivative of the three inverse trig functions. For y equals the inverse sine of 4x, our derivative is 1 over the square root of 1 minus 4x quantity squared times the derivative of 4x. And we get 4 over the square root of 1 minus 16x squared. In 7b, y equals the inverse tangent of x cubed. Our derivative is 1 over 1 plus x cubed squared times the derivative of x cubed, which is 3x squared over 1 plus x to the sixth. In 7c, y equals the inverse cosine of e to the negative x. Our derivative is negative 1 over the square root of 1 minus e to the negative x squared times the derivative of e to the negative x, which is e to the negative x times negative 1. The negatives cancel and we get e to the negative x over the square root of 1 minus e to the negative 2x. Problems 7d through g all have inverse trig functions involved. However, to take derivatives of these expressions does not mean that we will use primarily the inverse trig rules as seen above. As we've seen countless times before, there are other rules that we have to examine. The form determines which rule to use. We still have our power, product, quotient, trig, natural log, e, and a rules to look at. 7d reads y equals x inverse tangent of x, and that is a product rule. So we have first times the derivative of the second, which is x times 1 over 1 plus x squared, plus the second times the derivative of first, which is just plain old inverse tangent of x. Answer is x over 1 plus x squared plus the inverse tangent of x. 7e reads y equals the inverse sine of 2x quantity squared. This is a power rule. The 2 comes in front times the inverse sine of 2x times the derivative of the inverse sine of 2x, which is 1 over the square root of 1 minus 2x quantity squared times the derivative of 2x, which is 2. Put it all together and we get 4 inverse sine of 2x over the square root of 1 minus 4x squared. In 7f, y equals the natural log of the inverse tangent of the square root of x. The derivative of the inverse tangent would be 1 over the inverse tangent of the square root of x times the derivative of the inverse tangent of the square root of x, which is 1 over 1 plus the square root of x squared times the derivative of the square root of x, which is 1 over 2 square root of x. So our final answer would be 1 over the inverse tangent of x, quantity 1 plus x, times 2 square root of x. Finally, 7g, y equals x inverse sine of x plus the square root of 1 minus x squared. The first part is a product rule, and we have x times the derivative of the inverse sine, which is 1 over the square root of 1 minus x squared, plus the inverse sine of x, minus The derivative of the square root of 1 minus x squared is 1 over 2 square root of 1 minus x squared times 2x. And the first and the last term cancel, and we get that the derivative is the inverse sine of x. This is an interesting result because we know now that if we take the integral of the inverse sine of x, we get what the original problem G was. We have a couple of application problems using inverse trig. Number 8 reads, a particle moves along the x-axis with position function s of t equals the inverse tangent of t squared, where t is greater than or equal to 0. And we would like to know for what values of t is the particle speeding up. A particle is speeding up when the velocity and acceleration have the same signs. We start by taking the velocity of the inverse tangent of t squared, and we get 1 over 1 plus t squared squared times the derivative of t squared, which is 2t over 1 plus t to the fourth. And we're interested in where that's positive, and that means that t must be positive. So the particle could only be speeding up when the acceleration is positive as well. So we take the acceleration, squaring the denominator of the velocity, and upstairs we get 1 plus t to the fourth times 2 minus 2t times 4t cubed, and that gives 2 minus 6t to the fourth over 1 plus t to the fourth quantity squared. And we're interested in where that's positive. The denominator is always positive, so we're interested in where the numerator is positive, and that gives t to the fourth is less than 1/3, and therefore t must be a value greater than 0 and less than the fourth root of 1/3. 9 is a problem that most drivers can relate to. The base of a 20-foot tall exit sign is 30 feet above the driver's eye level. When cars are far away, the sign is hard to read because of the distance. And when they are close, the sign is hard to read because the driver has to look up at a very sharp angle. The sign, therefore, is easiest to read when the distance x, such that the angle theta at the driver's eye is as large as possible, as shown in the figure to the right. There are 3 things we'd like to do. We'd like to first write theta, we'd also like to find d theta dx, and then we'd like to find x when theta is at a maximum. We can write theta as the difference of 2 inverse trig functions. Theta will be the inverse tangent of 50 over x minus the inverse tangent of 30 over x. To take d theta dx, we first take the derivative of the inverse tangent of 50 over x, which is 1 over 50 over x quantity squared, times the derivative of 50 over x, which is negative 50 over x squared. We then subtract the derivative of the inverse tangent of 30 over x, which is 1 plus 30 over x quantity squared, times the derivative of 30x, which is negative 30 over x squared. And since we're subtracting that, we end up with a positive. We will then multiply every term by x squared, and we end up with negative 50 over x squared plus 2500 plus 30 over x squared plus 900. We would like to find the value of x when theta is at a maximum. So we take d theta dx and set it equal to 0. And we get negative 50 over x squared plus 2500 plus 30 over x squared plus 900 is equal to 0. Getting 30 quantity x squared plus 2500 is equal to 50 quantity x squared plus 900. And that gives 20x squared equals 30,000, and x is equal to 38.730 feet. So when x is 38.73 feet, we will have a sign that is easiest for the driver to read. We now work backwards for integration. If u is a differentiable function of x, and a is a constant, then the integral of du over the square root of a squared minus u squared is the inverse sine of u over a plus c. And the integral of du over a squared plus u squared is 1 over a inverse tangent of u over a plus c. You should memorize these formulas. Note that there is no formula that when you integrate you get the inverse cosine. That is because when you integrate du over the square root of a squared minus u squared, you could either get the inverse sine of u over a or negative the inverse cosine of u over a. We choose to write every one of these as an inverse sine. Here are three very simple problems. When doing problems of this nature, it is best to write out what a is, what u is, and then show work to get du and make sure that you can pull it off. Then simply apply the formula that is given. That's why these problems are mostly done by sheer memorization. So problem 10 asks to take the integral of dx over the square root of 1 minus x squared. This is in the form of du over the square root of a squared minus u squared. A is 1, u is x, du is equal to dx. So we immediately can write our answer as the inverse sine of u over a plus c, which will be the inverse sine of x plus c. 11 reads the integral of negative dx over the square root of 4 minus x squared. This is in the same format as number 10, except that we have a negative and a 4 instead of a 1. However, a is equal to 2, u is still equal to x, and du is equal to dx. The negatives comes along for the ride, and therefore we get negative the inverse sine of x over 2 plus c. You may want to take the derivative of this and show that we get negative 1 over the square root of 4 minus x squared. Number 12 reads the integral of dx over 1 plus x squared. Again, a is 1, u is x, and du is equal to dx. So by our formula, we have 1 over 1 inverse tangent of x over 1. And that simply gives the inverse tangent of x plus c. Here are three more problems that are a bit more complex and show that these types of problems need a little bit of work and thought before you can apply the formula. Number 13 reads the integral of dx over the square root of 5 minus 2x squared. It looks like this answer will be some form of inverse sine, but the numbers are not quite right. So we have to do some work. To find a, we ask ourselves, what squared is 5? And that is the square root of 5. To find u, we have to ask, what squared is 2x squared? And that is x root 2. Therefore, du is equal to the square root of 2 dx. We need our du into the problem, so we multiply on the inside by the square root of 2 and on the outside by 1 over the square root of 2 and get 1 over the square root of 2, the integral of the square root of 2 dx over the square root of 5 minus 2x squared. And this now becomes 1 over the square root of 2, the integral of du over the square root of a squared minus u squared.
That's our special form, so our answer is 1 over the square root of 2, the inverse sine of x root 2 over root 5. We can do a couple things here. First, we can write 1 over the square root of 2 as the square root of 2 over 2. And if we multiply both top and bottom by square root of 5, we get the square root of 2 over 2 inverse sine of x root 10 over 5 plus c. In 14, we have the integral of dx over 1 plus 4x squared. The form appears to give an inverse tangent, but the numbers are not quite right. The 4 kind of messes things up. So we let a equal to the number squared, which is 1, and u is what expression squared is 4x squared, which is 2x, and du is equal to 2 dx. We put a 2 inside the integral and a 1/2 outside the integral, getting 1/2 the integral of 2 dx over 1 plus 4x squared. And now write this in the form of a and u. 1/2 the integral of du over a squared plus u squared. So by our formula, we get 1/2 times 1 over 1 inverse tangent of 2x over 1. Which is 1/2 inverse tangent of x plus c. 15 reads the integral of 2 over 4 plus 9x squared dx. This problem looks like number 14, but it is even more complex. We start by finding a, the number squared, which is 4, and that is 2. U is the expression squared to get 9x squared, which is 3x, and therefore du is equal to 3 dx. So we rewrite our problem as 2 over 3, the integral of 3 dx, which is our du, over 4 plus 9x squared. And now everything is in terms of u and a, 2/3 the integral of du over a squared plus u squared. Applying our formula, we have 2/3 times 1 over a, which is 1 over 2, inverse tangent of u over a, which is 3x over 2. Final answer is 1/3 inverse tangent of 3x over 2 plus c. 16 and 17 appear to be problems that cannot be integrated. And yet they can, using a technique that you learned in Algebra 2 called completing the square. 16 reads the integral of dx over x squared plus 10x plus 29. We are going to write the denominator as x squared plus 10x plus 25 plus 4. Why? This is the technique of completing the square. We take half of the x term, which is 10, and divide it by 2, and we get 5, and square it. That gives us 25, and since we have a 29, we will then add a 4. So now this problem can be written in the form of the integral of dx over 2 squared plus x plus 5 quantity squared. And this is in the form of the inverse tangent formula, where a is 2, u is x plus 5, and du is equal to dx. So by our formula, this will be 1/2 times inverse tangent of x plus 5 over 2 plus c. 17 reads the integral of dx over the square root of 8x minus x squared. This appears to be an inverse sine problem when we integrate, except for the x. Everything would be fine if it was just a plain old 8, but we have an 8x. And yet this problem can be done by completing the square. We want to write this denominator as the square root of a squared minus u squared. So we need some expression that when squared gives us x squared minus 8x plus some constant. So we complete the square and realize that the constant is 16. So we can write the denominator as the square root of 16 minus quantity x squared minus 8x plus 16. Now we can write this with a equaling 4, u equals x minus 4, and du is equal to dx. We have the integral of dx over the square root of 4 squared minus x minus 4 quantity squared. And that is our special form for inverse sine. So our answer is the inverse sine of u over a, which is x minus 4 over 4 plus c. These problems are hard. You know that since it's in this section on inverse trig functions, it will probably use an inverse trig function. But when you just see this integral, no one is going to tell you what to do. So you have to add this technique of completing the square to your bag of tricks for integration. Finally, don't fall in love with inverse trig. Not all integral problems with integrands having a denominator in the form of the square root of a squared minus u squared or a squared plus u squared involve inverse trig. You have other techniques at your disposal, and you should not try to force a problem into an inverse trig one when it isn't the correct form. In reality, inverse trig should be a last resort. Always think about typical u substitution first. 18 through 20 appear to be inverse trig problems, but neither of them are. Number 18 reads the integral of x over the square root of 5 minus 2x squared dx. If the x were not in the numerator, this would be in the form of an inverse sine. But it is. So we're going to do typical u substitution. U is 5 minus 2x squared. Du is negative 4x dx. We multiply by a negative 4 on the inside and a negative 1/4 on the outside, getting negative 1/4, the integral of u to the negative 1/2 du. And integrating, we get negative 1/4 u to the 1/2 divided by 1/2, which is multiplying by 2. And our final answer is negative the square root of 5 minus 2x squared over 2 plus c. 19 reads the integral of e to the x over 9 plus e to the x dx. If it weren't for the e to the x upstairs, this would look like an inverse tangent problem. But since the e to the x is there, we will do this by u substitution. U equals 9 plus e to the x, and du is equal to e to the x dx. And this problem is very simply in the form of the integral of du over u, which is the natural log of the absolute value of u, or the natural log of 9 plus e to the x plus c. No need for the absolute value signs because e to the x is always positive. 20 reads the integral of cosine x over the square root of 1 minus sine x dx. Again, if it weren't for the numerator, this would appear to be a problem in the form of an inverse sine. But since the numerator is there, we will do this by u substitution. U is 1 minus sine x, du is equal to negative cosine x dx. We compensate by putting a negative on the inside and a negative on the outside and writing this negative integral of negative cosine of x, 1 minus sine x to the negative 1/2 power, and that is negative the integral of u to the negative 1/2 du. And when we integrate, we get negative u to the 1/2 divided by 1/2, which is multiplying by 2. Final answer, -2 square root 1 minus sine x plus c. Problems 21 through 23 are even more complex and will involve several integration techniques, one of which may be inverse trig. 21 reads the integral of x plus 2 over the square root of 4 minus x squared dx. To do this problem, we are going to break it up into two integrals, the integral of x over the square root of 4 minus x squared dx, and the integral of 2 over the square root of 4 minus x squared dx. We won't go through all the steps in each integration, but the first one is done by u substitution, and the second one can be done using our inverse trig. Final answer is negative square root 4 minus x squared plus 2 inverse sine of x over 2 plus c. I invite you to go through the steps of each integration. 22 reads the integral of x plus 2 over x squared plus 4 dx. This is similar to 21. And a good general rule is that when you do have an integral with a numerator that has several terms, you can break it up into several integrals using the same denominator. So we write this as the integral of x over x squared plus 4 dx plus the integral of 2 over x squared plus 4 dx. The first one can be done with a natural log, u substitution type problem, and the second one can be done with an inverse tangent, inverse trig type problem. Final answer is 1/2 natural log of x squared plus 4 plus the inverse tangent of x over 2 plus c. Again, I invite you to go through the steps of each integration. 23 reads the integral of x cubed over x squared plus 1 dx. This appears to be an inverse tangent problem, but again, we have that pesky x cubed up top. When you have a higher power on top of an expression with a lower power, a good technique is to do long division. If we divide x squared plus 1 into x cubed, we get x with a remainder of negative x. So this integral can be written as the integral of x dx minus the integral of x over x squared plus 1 dx. The first integration is a simple power rule. The second is a typical u substitution. Final answer is x squared over 2 minus 1/2 natural log of x squared plus 1 plus c. This problem appeared to use inverse tangent, but never did.